And then the last half of the talk is going to be a bit more specific and hopefully interesting to the experts. Yeah, cool. So, why am I interested in classical simulations of quantum computers? There are two reasons. The first, which is the most interesting for me, is by understanding the bits of quantum mechanics that we can simulate efficiently, we can try and understand the bits that we can't. The bits which are, in some sense, like hard for classical computers to simulate are the bits where quantum computers have some advantage over classical computers, if there are any. And the second reason, which is probably more interesting to most other people, is practically, if you're designing quantum algorithms, or if you're trying to build a quantum computer or do quantum stuff, it's very useful to be able to use your classical computer to simulate a quantum computer, because every single quantum information theorist or experimentalist has a classical computer on their desk, and most do not have a quantum computer on their desk. So simulations are useful. Fantastic. I'm going to talk a lot about quantum computation in this kind of general abstract sense. And the idea I want you to have in the back of your head is, so this is the Himalayas, is that there's some kind of landscape which consists of all of the possible quantum computations you can do. And the analogy is that the height above sea level, or maybe the difficulty of getting to some point in the Himalayas, corresponds with how hard it is for a classical computer to simulate a computation, right? And we want to explore this landscape. We don't really know anything about it. We believe that something like Shor's algorithm is hard for a quantum computer to simulate. And we know that some things are easy. But yeah, we're trying to kind of map this landscape of computations. And hopefully this is a goal that you're vaguely interested in, if you're here. So for the purposes of this talk, I'm a theorist. So this is a quantum computer, schematically. And the point is that the quantum computer has classical inputs. So I give my computer classical data, and I get out of it classical data. This is kind of essential from a complexity theory point of view, because I want to be able to compare my quantum computer with a classical one, right? So I have to be giving it classical problems and getting classical answers to those problems, right? I'm going to ask my computer, I don't know, for the best route through some graph or whatever. I want classical stuff. You can also think of a quantum computer as a machine that processes quantum data and gives you quantum output. That's fruitful and useful and cool. I'm not doing that here. So this is a quantum computer. And for anyone who is not an expert in the audience, for the purposes of this talk, a quantum computer has an internal state, which I'm assuming is a pure state. It's a 2 to the n dimensional vector of complex numbers. It defines what my quantum computer is doing at any moment. And at any time step, I'm going to update the state by multiplying it by a matrix. I update the vector by multiplying it by a unitary matrix. And then after we do this a few times, we measure some observable. And so we get outputs from our quantum computer just by the Born rule. So for the purposes of this talk, it's not... Oops. Over here. Sorry. Okay, did this flash or do something strange? I saw it out of the corner of my eye. Yeah, so for the purposes of this talk, it's not always the case, but just for this talk, an observable is just associated with an orthonormal basis, and outcomes follow the Born rule. So you get some outcome x with probability given by the inner product squared. If you want to be more general and talk about density matrices and POVMs, whatever you can, but it's not relevant for this talk. So this is what quantum mechanics essentially is for this talk. 2 to the n-dimensional complex vectors, we apply unitary matrices, we measure observables by this rule. Fantastic, here's an example. So this is a quantum circuit. There'll be a few diagrams like this in this talk. On this diagram, we have an input or zero state, so it's 0 on both, so I should say each of the horizontal lines in this diagram represents a qubit. Each of the boxes represents a gate. This funny thing in the middle is a 2-qubit gate, a C0 gate. And these guys on the end represent measurements. So these are my input states, both 0. My Hadamard matrix, my unitary. This is a 2-qubit unitary, the CX. And these are some observables. I'm just going to run through this circuit super quickly. So the all-zero state looks like this, written out as an explicit vector. This is what this is. We apply a Hadamard matrix, or the Hadamard gate, which just applies this transformation to the state. I apply a CX, which gives you this state now. And then I do a measurement according to the Born rule, which gives me, 4 possible outcomes for a computational basis measurement, with probabilities that turn out to be 1/2 for the all-zero state, 0 for 0, 1, and 1, 0, and 1/2 for 1, 1. So this is an example of quantum computation. And I hope this kind of vaguely makes sense to everyone in the audience. Yeah, OK, good. So a quick note on complexity theory. So here are some complexity classes, which I've drawn in a nice diagram. So these funny symbols, I assume most of you are familiar with them. This is just an inclusion. So this says that P is inside NP, NP is inside MA, MA is inside QMA. All of these things are inside P space. So this is this diagram. So here are some relevant complexity classes. Most of you, I think, have heard of P versus NP, probably. This is an open problem in complexity theory, whether P is equal to NP. Loosely speaking, P is the things that you can solve in classical time on a deterministic classical computer. So if I have a normal classical computer with no random numbers, I can solve problems in P. If I have a normal classical computer and I have a random number generator, I can actually solve problems in BPP, which is over here, which is bigger. So BPP is probably the complexity class that you can do realistically classically. BQP, on the other hand, I'm not going to define it formally, but BQP is essentially the complexity class that you can realistically do if someone gives you a universal fault-tolerant quantum computer. So if we get the holy grail of my field, which is we build a really good quantum computer, we expect to be solving problems in BQP using it, probably. MA is a sort of generalization of QMA. I don't want to talk about it too much. QMA, which is the quantum version of MA, is essentially, you can think of this as the quantum variant of NP. So this is like the problems where you could verify if someone...
What MA stands
MA actually stands for Merlin Arthur, which is why I didn't say it. It's not a very useful name. So this is the problem. The idea is Merlin is a wizard. The idea is Merlin gives you the answer to your problem. And in polynomial time on a quantum computer, you can verify Merlin's answer. So you get an answer magically, and you can verify it using a quantum computer. So this is MA and QMA.
Is MA like checking if so like in cryptography, you have to prime numbers. If you get them, and you can easily check whether the number is the product of them or not. Is it this class or?
Yeah, that would be in NP actually, probably. But
Okay, so it's not.
yeah, this is a generalized NP. You can think of it as I think most of the generalization from NP to MA is that you can have multiple rounds of communication. So Merlin gives you the answer. You can ask Merlin more questions, and he can tell you more things. Yeah. OK. And then here we have some standard classical complexity classes. So right over here, we have things you can solve on a classical computer if you have access to polynomial amounts of space, like memory, in unbounded amounts of time, just polynomial space. So the P space is a huge complexity class containing many bad things. However, despite all that we know about complexity theory, we actually don't know if P equals P space. So it might be that all of these are exactly the same and P equals P space. This is open. No one knows. So you may have heard that P versus NP is a big open problem. P versus P space is a big problem. That's how far away we are from knowing anything about P versus NP. For the purposes of this talk, I will occasionally say things like, I'll just assume that BQP is bigger than P and QMA is bigger than BQP. I'm going to assume that these complexity classes are actually not the same, just because it makes it easier to talk if you have to avoid constantly saying that these things might be the same. So yeah, I will do that just as a lazy shorthand. I'm just going to talk as if these inclusions are strict. But they might not be. Oh yeah, sharp P I want to mention quickly. Sharp P is the problem of counting the number of solutions to problems in P. So P is finding a solution to some problem, like a route through some map. And sharp P is the problem of counting how many solutions there are through the problem, through the map, for example. The hash means, it's also called counting P. This will turn up, I think, on the next slide. So this is all I want to say about complexity theory. I want to talk a little bit about what simulation means for the purposes of this talk. So there are a few different ways you can think about doing simulation. You can do weak simulation or strong simulation. Weak simulation is your classical computer is pretending to be a quantum computer. So every time you run this program on your classical computer, you get a random answer from the same probability distribution that the Born rule would give you. And strong simulation is just computing probabilities directly without doing this sampling thing. Then you can do either of these, either approximately or exactly. And you can do approximations to relative or absolute error. These are different things you can do. So for the purposes of this talk, I am going to be doing absolute error approximations to Born probabilities. So we're in this thing here with absolute error. Mostly because that's what I know how to do. In fact, it turns out that the methods we use also give you weak simulation to absolute error as well. But yeah, I'm focusing on this box here. And the reason I do absolute error rather than relative error is because if we go back to the complexity theory, absolute error essentially, I can't use my, I don't know the mouse. Absolute error gives you BQP. So absolute error is like as hard as BQP. Whereas relative error approximations here would actually be sharp P. So computing relative error approximations is a sharp P complete problem. So we don't want to do that. It's very hard. So yeah, absolute error approximations to Born probabilities is what, well, that's what simulation means for this talk. Is it okay?
No, just
okay, sure. Okay, so the main ingredient, the main thing I want to tell you about today are these things which I named computational resource theories because no one else named them, and I'm bad at naming things. And this is essentially a chunk of quantum mechanics which you can efficiently simulate classically. So I take the whole wide space of quantum mechanics with different states and observables and measurements. I just restrict myself to some small, tiny set which I can simulate efficiently classically. Okay? So I have a subset of states. I have a subset of operations, unitaries, for example, which keep you inside that subset of states, and some observables that you can measure, such that you can do everything efficiently in polynomial time. So here's an example. The first example I want to show you is entanglement. So if you imagine a quantum computation which has, I don't know where the mouse went, but okay. If you imagine that we have a...
The top button.
Huh?
You press the top button?
Yes, I did. I am currently pressing the top button. Yeah, it's there. Okay, cool. It was off the side, I think. Okay, so if I have a computation which is like this, it has this block structure, right? So I have blocks of a fixed size. I have k blocks. I don't care how many blocks you have, such that my circuit doesn't have any gates which cross the boundaries between blocks, right? So I can do anything in the first block, but it doesn't talk to the second block or the third block. Then this setup, for fixed block size, can be efficiently classically simulated in polynomial time. And it's very simple and stupid. What you do is you just simulate each block completely separately, independently, and multiply the answers together. So as long as the blocks are not too big, you can do this. For fixed block size, you can do this. And you can see I wrote at the bottom, so you can do this in order k times 2 to the n. So each block takes me time 2 to the n, and there are k blocks. I just do them one after the other. So this is quite cool. So yeah, the resource theory of entanglement is essentially one of these efficiently simulable subtheories. The second example, which is ubiquitous if you've studied anything in quantum information or computation, is the n-qubit Clifford stabilizer subtheory. And this is a bit technical if you've not seen it before. But what you do is you define the Pauli group, which is the group of all Pauli matrices. You then define Clifford operations, which are unitaries, which map Paulis to Paulis. So a unitary is Clifford if it takes something in the Pauli group and maps it to something in the Pauli group. Or rather, it takes everything in the Pauli group to something in the Pauli group, I should say. And if you define this set of Clifford gates, then you end up essentially with one of these efficiently classically simulable subtheories. It's very well studied. It turns up everywhere. It turns up in quantum error correction. It turns up all over the place. It's very cool and useful and ubiquitous. And yeah. So it was shown already in 1998 that this setup is efficiently classically simulable in polynomial time. And in 1998, this surprised a lot of people because people already in the 90s had this idea from my previous slide. They were like, if my quantum computation doesn't have entanglement like between blocks like this, then you can simulate it classically efficiently. And so people in the 90s kind of thought, maybe that means the entanglement is the magic thing which gives quantum computers advantage over classical computers. And then Gottesman and some other people came up with this n-qubit Clifford stabilizer subtheory, which has arbitrary amounts of entanglement. It has a lot of entanglement, a lot of entangled states, but you can still simulate it efficiently classically. And so this kind of essentially killed this idea that entanglement was the thing which gives quantum computers advantage over classical computers. Because here we have this thing with loads of entanglement, but you can still simulate it. I'm not sure if that's entirely a fair thing to say, because the entanglement in this subtheory is quite specific and limited. But okay, at least it means that it's not as simple as we thought. It's not just entanglement. And the final example I want to give is really stupid, just so everyone can follow it. So if I restrict my quantum computation completely so that the only states I have in my subtheory are pure computational basis states, so labeled by binary vectors, the only unitaries I have are essentially permutations of computational basis vectors. So the only unitaries I have map computational basis states to computational basis states. And the only observables I have are just the computational basis observables. Then this subtheory of quantum mechanics is actually just classical Boolean logic circuits. They're the same. And so obviously you can simulate it classically efficiently. And this is one of the ways of defining the resource theory of coherence. There are others, but this one, okay, is one of the ways. It's how they do it in this paper. Yeah. At this point, I just want to emphasize this notation. So on this slide, I'm calling things free if they're inside my little subtheory where I can simulate things. So free things I can simulate. And later, I will call things resourceful if they're not in the subtheory. So free is inside the subtheory, resourceful is anything else. Okay, that's just some notation for later. Okay, fantastic. And here are a bunch of other examples. So these are just ones I cooked up. You can cook up many other examples. So for example, log space circuits here. There's a stupid classical algorithm that simulates a quantum circuit in exponential time 2 to the n. So if n is logarithmic in something, then 2 to the log is just a polynomial. So yeah. Here are just some so these are just some examples I know about. It turns out, in fact, that these two examples are the same computationally. These are computationally equivalent. And if you look ahead in my, if you look ahead at the top of the slides, above the slides, you'll see that we're going to talk about fermi-Leitner optics later. Okay. So I told you about these little subtheories a lot just now. I guess the natural question is, why should you care about them? And maybe I should have put this before I told you about them, so you actually pay attention. But okay, you should care about them. And here is why. Because they function as base camps in this landscape of quantum computation I showed you earlier. So the properties of a base camp are that it's relatively easy to get to. You can walk to Everest Base Camp, probably, without too much difficulty. And the existence of Everest Base Camp makes it easier to get up Everest, right? It would be quite hard to get up Everest without the existence of the base camp. And so the idea is that these little subtheories, not only are they easy to simulate themselves, but they make stuff which is close to them also easy to simulate. Okay? And this is why you should care about them. As an aside, can I show this? Yeah, Everest Base Camp, the thing is actually just here in the corner of this picture. This is Everest Base Camp, somewhere here. It's very small in this picture, but I like the picture, so fantastic. So yeah, the idea is that the existence of these subtheories will make it easier for us to simulate other stuff. So here's an example. Here is a quantum circuit which just has 2 blocks. I know that there's only 3 qubits in each block, but I want you to imagine there's 30 qubits in each block. So if there's 30 qubits in each block, I can simulate this setup with my laptop. I think doesn't have 16 gigabytes of memory, but okay, I can find a computer with 16 gigabytes of RAM, and I can simulate this setup. And I just simulate the first circuit completely by itself, and then I simulate the second circuit completely by itself. Each simulation takes 16 gigabytes of memory, but it's fine. Sorry, was there a question? Okay, no, sure.
What kind of simulation do you refer here to?
So this would just be keep a vector of 2 to the n complex numbers in your computer. So this number is 2 to the n, and then it's 2 64-bit floats for each complex number, right? So it's real imaginary parts of it. So you just store a long vector and do matrix multiplication on your vector and do everything very simply. And the only smart thing you do is you do it separately for the first block and then the second block and multiply the answers together at the end. Right? This is all you have to do here. On the other hand, if I add a single gate, so if you look at the difference in the slide, I added this one gate over here, then I can't do this anymore. Then I have to simulate everything together. I have to simulate a 60-qubit quantum circuit. And this requires, I think, 17 billion gigabytes of RAM. I did this calculation yesterday. I think it's right. And this is, you should think of yourself, this is objectively stupid. I added one gate, and now I have to simulate this whole circuit together. I can't do this one block, then the other block thing. And I now require 2 to the 60 times 128 bits in my computer, and it's impossible. right? So doing this via like standard state vector simulation is stupid, okay? You should, yeah, intuitively, it is stupid. So what do you do instead? What you do instead is, this is me just saying this is silly. What you do instead is the first part, or the second part of my talk title, adding things up. You decompose this CZ gate I added as a sum of local gates. So this first S here acts over here on this qubit. This second S here acts over here on the second qubit. This S dagger acts on the first qubit. This S dagger here acts on this qubit over here. So CZ you can write as a sum of local gates. And now I can do exactly the same block simulation I did before. I do the block simulation with this term. I do the block simulation with this term. I add them up at the end. This goes by the quite grand name of hybrid Schrödinger-Feynman simulation for historical reasons. And it's kind of the obvious thing you should do, essentially. So yeah, this works, I think, yeah. And the scaling of this is if I had, instead of just one CZ gate, I had k of them, it goes as 2 to the k, right? Because I have k terms, I multiply out the brackets, I get 2 to the k terms. And this actually led to a fun debate in about 2019, 2020. So if you remember back to then, if you were following quantum stuff back in 2019, Google announced they had achieved quantum supremacy. And a little bit later, so they announced that they had done something on their quantum computer very quickly, that it would take a classical computer, I think, 10,000 years to do. And a little bit later, some scientists at IBM came, and they're like, actually, we can simulate this in our classical computer in 2 days. And what they used was essentially this with some more tricks. So they took all the entangling gates in Google's circuit, they wrote them as local gates, and they added everything up. They did a lot more fancy tricks than that, and you have to for those circuits, but this is the basic idea of what they did. So that's quite cool.
But you still need to add it at the level of amplitudes, not probabilities.
Yes, you have to add it to the level of amplitudes, yes. Yes, you do. But that's fine. Add up complex numbers,
Yeah,
it's okay.
Probably fine, but still, I mean, it's something that you need to pay in the end. When you compute probabilities, yes, you at least have like cross terms also between this.
Do you have cross?
Or no?
I think you do not have cross terms if you do this in the right way, but I could be wrong. I should know that.
But then it's quadratic anyway.
I don't, yeah.
So it's not too bad.
Okay, yeah. But I think that, yes, but that quadratic, it's a quadratic in 2 to the k, right? Which is pretty bad. I think it's just 2, I'm pretty sure it's just 2 to the k and not a quadratic in 2 to k.
Okay.
At least with the methods you should use. I'm pretty sure that's what IBM did, but I haven't read their paper in a huge detail. Okay, yeah. I just want to take a quick aside from the story now and talk to you about gadgetization. Huh? Yeah, sure.
Because here you showed an example for 2 weakly coupled blocks, right?
Pardon, sorry, could you speak a bit louder?
Two blocks.
Yes.
And what happens if there are more blocks?
If there are more blocks, so for every block that doesn't talk to each other, you get essentially a polynomial multiplying your runtime. So here, if there are k blocks, your runtime will multiply by k. And then you just pay an exponential cost for the number of entangling gates between them. So it's just all of the entangling gates, each entangling gate between blocks will multiply your simulation cost by 2, basically. Right? Yeah. Or possibly 4, if rough was correct. But I think 2. I'm pretty sure 2. Okay, good. So gadgetization is a useful trick. It's maybe not so useful actually in practice, but it's very useful in theory. Because gates are big and complicated and states are a bit smaller and easier to deal with. So we do gadgetization, sometimes also called gate teleportation. And what we do is we say, if we have non-free gates in our circuit, I replace them by a bunch of free gates and an input non-free state. So I can think about stuff in terms of adding up states, not adding up gates, and that makes my life easier. So here is an example. This is a CZ gate. This is the same decomposition as before, essentially, except that I have replaced my I've replaced it essentially with, instead of having a non-free gate over here, I have a non-product state over here. So this is an entangled state across these 2 qubits. along with a bunch of free operations. So other than the state, everything here is split nicely between the two blocks. The state is the only thing that spans across the blocks. And this just means that I can do things by thinking about the state, not thinking about gates. It makes my life easier. Yeah, you can do the same in the Clifford plus T thing. So I told you about the Clifford stabilizer subtheory earlier. If you take the Clifford stabilizer subtheory and add T gates to it, you get something universal. You get something that can do any quantum computation. Then you can take those T gates and replace them by free operations. So the CDX is free, and this 0 thing, these live in the Clifford subtheory. And then an input non-free state. Good. So this is not, there's not like a theorem that this always works, but it seems to work in every example I've tested, I've looked at. You can do schedulization and think about states instead of gates. And a fun little micro optimization you can do actually is you can flip these gadgets around, and instead of measuring, or instead of inputting magic and measuring free stuff, you can input free stuff and have, so in this circuit, everything is free up until this last measurement here. And okay, there are some reasons this is good. This lets you do some essentially polynomial optimizations to your simulation algorithm. Okay, cool. Hopefully that makes sense. So okay, yeah, the basic idea of simulating non-free resourceful computations then is you gadgetize everything that's not free in your circuit. Then you write this input magic state that you need to make these gadgets work as a sum over free states. You only really care about situations where your free states span the state space. So there is a linear combination of them that works. And your simulation cost essentially goes with the number of terms in this sum. Yeah, you can. So so what you do essentially then is you do an efficient classical simulation, a simulation entirely in the free subtheory for each of the terms in this sum, just one for each term, and you add the results up at the end, and you're happy.
So, can I
Yes.
ask something? So, like when you presented in the very beginning, say, problem of computing Born-rule probabilities.
Yes.
Like those quantities, they are like insensitive to global, like to phases, right?
Yes.
And like here, I sort of, yeah, you clearly need access to this phase, right? Because you write.
Yeah, you don't care about global phases. I can obviously multiply this sum by a whole global phase, and I don't care. This is exactly the same as before. But I care about the relative phases between the different things. Yeah. And now if I think about doing one simulation, each simulation that I do for each term in this sum, in those guys I have to keep track of the global phases. Yeah, and this is exactly what we do.
My question is like, are you aware? Because like those classes of that are easy to simulate. Let's say they. How to phrase like, do you know an example where it's easy to compute stuff without like relative phase, but it becomes complex where you have to care about the relative phase?
No, I don't know any such example. So one stupid thing you can do, no matter what your subtheory is if you know there is a state that your state never becomes orthogonal to throughout the entire computation, you just pick, like, let's say you're doing something, I don't know, close to the ground state of some Hamiltonian or whatever, then you can always just have this as a reference, right? And then you can always keep track of the phase relative to that. So I think that should like hand-wavingly work, and then you have to do more advanced stuff otherwise, but yeah. I don't know if
I
it's...
expect that perhaps it's always possible.
I think it's always possible. I think it's always possible to keep track of these phases in a bad way. I don't know if it's possible to keep track of them in a good way. Okay. Yeah. So a slightly more complicated example is an idea is that we're not going to do this sum exactly. We're just going to do this sum with some epsilon error. Because in any case, our quantum computer is going to be slightly noisy. So our classical computer may also as well be slightly noisy if it makes our life easier. Yeah, and once again, we just have a simulation cost that goes is the number of terms in this sum. Yep. Okay, good. So all we have to do is find these approximate low-rank decompositions of our magic states, right? That's true. We do. That is correct. But it turns out this problem is wildly hard. I think it's NP hard. I think it's NP complete even. But anyway, it's hard in general. Essentially because our free subtheories contain many more states than a simple basis, most of them. So there's like a lot of ways you can write this sum in different ways over different parts of different free states. And it's very not obvious how to find a good one. So here's an alternative which kind of upper bounds this rank, this k prime, called the extent. So I define the extent to be the minimum of this 1 norm squared term here, and in like 2 slides' time, I hope you'll understand where the 1 norm squared comes from here, over all decompositions of my target state in terms of free states. So this is the extent. It's the infimum of a 1 norm squared. It turns out to be the minimum of a 1 norm squared. Okay. As physicists, we hate the 1 norm, right? We love the 2 norm, but it turns out to be a 1 norm squared that gives you the right thing. Here is roughly speaking why. So I'm going to take this decomposition I had on the previous slide of my state. I'm going to divide each alpha I by the total 1 norm of the alpha vector. And I'm going to rescale my states in this way. And the reason I do this is because this guy here, the absolute value divided by the 1 norm, is a probability distribution. And I'm going to do some like random sampling, and I'm going to use concentration inequalities from probability theory, right? And the important point on this slide is that since I divided by a 1 norm here, each of my states fi got multiplied by a 1 norm here. So my states now become really long if this 1 norm is large. And in general, they will be. Yeah, so then what you do is you take a bunch of random samples from this probability distribution and compute the sample mean to give an approximation to the target state. And OK, the slides are botanical. The overall takeaway is the Houghton's inequality tells you how well the sample norm approximates the true norm. And the important point on this slide is I require that all of the vectors here that I'm sampling have a 2 norm squared less than m. On this previous slide, I multiplied all my vectors by alpha 1 squared, the 1 norm, sorry. So all of these vectors, if they start as normalized vectors, now have 2 norm given by the 1 norm of alpha squared, right? So m is now the 1 norm of alpha squared, and m appears here in something which tells me how well my approximation is, how good my approximation is. In particular, m is directly competing with s, which is the number of samples I have to take from a probability distribution, right? So if m is very big, I have to take many samples, right? And that means if the 1 norm of alpha squared was big, I have to take many samples. And that is why I care about this extent thing, which is a weird 1 norm squared.
One question, mu here is the target state, or is it?
Here what? Oh yeah, here mu is the true expectation value, which is going to be the target state I have, yeah. Yes. So this will be like the input magic state, this vector which I gave as an input to my gadget. OK, awesome. So this is why I care about 1 norm squareds, because they appear in Houghton's inequality like this when I do this trick. Fine. So that was essentially the background. This is like the general stuff, which isn't specific to any particular resource theory. Roughly how I think about classical simulation. And I'm now going to, let me see. OK, I'm now going to a little bit faster, talk about some specific stuff which I did with Michał, and some stuff I did alone. To do with this specific example of fermionic linear optics, where we worked out this program in this one case. So I'm going to reference these 3 papers. The first 2, the top 2, actually appeared in arXiv on the same day last year, because we spoke to each other about them. We knew we were both releasing them on the same day. The third one I wrote about a year later. And the first 2 give classical simulation algorithms for quantum circuits where most of the circuit is FLO, fermionic linear optical, and I have some non-FLO magic in there as well. The bottom one, so yeah, that's the first 2. The third one, the bottom one, I worked out essentially how this extent scales with the number of magic states in your circuit, which was kind of cool. Cool, so a very quick overview of FLO. So if you have some creation and annihilation operators like this, so A dagger is a creation and A is an annihilation operator. There are n of them, labeled 0 to n minus 1. You can cook up these things called Majorana-Fermi operators, just like this, which are let me think. They're Hermitian, they're unitary, and they satisfy this nice anti-commutation relation. And if you are a quantum information theorist and you think about things which are Hermitian and unitary, your first thought is always the Paulis. And it turns out that these are closely related to Pauli operators. So if you choose, JW here is the Jordan-Wigner transformation. I should have written their names out in full, but they were too long, so I didn't. So this is the Jordan-Wigner transformation. You can map the first Majorana fermion operator onto a Pauli X on your first qubit. The second Majorana fermion is just a Pauli Y on your first qubit. The third is a Z followed by an X, and so on. So if you like quantum information, then these Majorana fermions, which you've probably not seen before, are just very closely related to the Paulis. You can think of them as strings of Paulis. Okay, so fermi-linear optics, the subtheory which I'm going to be working on, is defined by essentially this relation. I say unitary is in FLO, it's free, it's FLO, if it satisfies this relation. So U is free if I stick it on both sides of a Majorana fermion, and I get a sum of Majorana fermion operators. It turns out if you just demand that this is a sum, then you end up with R being real and special orthogonal as a consequence. So yeah, FLO unitary is map Majoranas to sums of Majoranas. If you are a quantum information theorist, this will probably remind you of the fact that Cliffords map Paulis to products of Paulis. FLO operators map Majoranas to sums of Majoranas. It's kind of an analogous relation. So this is FLO. These are the unitaries. And then the free states are just anything you can acquire, you can get from a computational basis state by hitting it with one of these unitaries. And free measurements are just computational basis measurements. So this is FLO. So way back in 2002, Terhel and De Vincenzo showed that you can efficiently classically simulate this setup. Yeah, you can compute probabilities of things which are just FLO. Yeah.
So this is related to this Clifford group, or it's different?
It's different to the Clifford group. It plays a similar role in the subtheory. Like it's a different subtheory, which is like not the same.
Because you said, I mean, that the C's are essentially some Paulis.
Yes.
So then one could think that there is a really close connection between this Clifford and this no. But it's
there are connections, but I'm not sure how close they are. Yeah. Just because this relation is different, so it's sums, not products. There are some relations, like it turns out that the maximally the guys, at least in some examples, which are maximally far away from being FLO, are stabilizer states, it turns out. So I don't know. There's some relation, but maybe not an obvious one. Yeah. Okay, so then a few years later, it was shown that if you take FLO circuits, these restricted circuits that have this form, and you add input magic states, which look like this, then you end up with a setup that's universal for quantum computation. And the way this works is exactly with the gadgetization type argument I showed you before. You stick these input magic states into a gadget, and you get stuff that's universal for quantum computation. In fact, if you only have phi equal to pi here, already that's universal. But okay, I can have phi not equal to pi as well. As long as phi is not a multiple of 2 pi, it's universal. Fantastic. So all I have to do is understand how to decompose these magic states in terms of FLO states, and I can kind of see what happens. So yep, it turns out you can decompose these magic states in terms of free FLO states. This decomposition is incredibly obvious. It's in fact an orthogonal decomposition. Yep, so this is what you do. And it turns out that this decomposition I just showed you is optimal in terms of this 1 norm squared measure I had a few slides ago. So this decomposition, if your algorithm works according to this sampling Hofstad's inequality type argument, this decomposition on the previous slide is the best one for these input magic states. And so Mihao and Kamil Kozhekva and Diaz and Robert Koenig in Munich independently showed that in addition to being optimal for a single copy of a magic state, this works the same if you have 2 magic states. And then like a year later, I showed it works if you have as many magic states as you like. In fact, this works if you have not just magic states, but any 4-qubit states here. This works. and the magic states are 4-qubit states, so we're happy. Incidentally, it might not be incredibly obvious that this should be multiply here. Maybe you think it should be add, I don't know. The reason it has to be multiply, essentially, is if we showed it was add, then we would have a classical simulation algorithm that could simulate quantum computers in polynomial time, and then people would be sad. So it has to be that if you have m of these, like the runtime goes as like psi to the m, right? Otherwise, we would have shown that you can simulate all quantum computations in polynomial time, and we didn't do that. So yeah, multiply is the right thing here. Good. Very roughly, these results come from some representation theory that Michał and I think Marek Kusch worked out. Is that right? Yeah. In about 2014. And the answer turns out to be that 2 to the 4 divided by 2 is 8, and this is also 2 times 4. So this is where we get our nice results from. Yeah, 2 to the 4 divided by 2 is the state space of a 4-qubit system. If I divide it by 2, because fermion optics respects parity, fermions, they have parity relations. So essentially my state space gets divided by 2 because I have a parity restriction. So this is what we have on the left-hand side, is 4 qubits divided by parity, essentially. On the right-hand side, what we have is this 2 n-dimensional special orthogonal matrix I mentioned before. And it turns out because these are in dimension 4, both 8, FLO works really nicely on 4-qubit systems. And you can work out these things really, very exactly for 2-qubit systems. If we go back to these results, if you replaced my magic state with a 5-qubit state or a 7-qubit state, I can't prove anything anymore. I only know things about this 4-qubit system because of this nice relation. It's a wildly open question. No one has any idea how these things behave in dimensions other than 4 and multiples of 4. Good. So I have 10, 15 minutes left, is that right? 10. Yeah, okay. 10 minutes, okay. Cool. So the rest is very fast, that's okay. Yeah, how does our simulation algorithm work? The one that me, Michał, and Kamil, and the guys in Munich came up with independently. This was already mentioned a few times, but essentially, if you're adding up state vectors, you have to know the phases between them. Because, if the phase is 1, I have to add it, and if it's -1, I have to subtract it, and these just give me very different answers. So for adding things up, you have to keep track of the phase. But if I'm relying on this adjoint action in the way that Tuchel and Divincenzo did, any phase that's in U here will just cancel out because U dag will have the opposite phase, and so this is completely phase insensitive, this equation. So I can't use the same methods that Tuchel and Divincenzo did if I want some way of keeping track of the phase. And so we came up with a new algorithm that lets you simulate FLO in polynomial time while keeping track of the phase. And this is the main technical contribution of our paper. Sorry. So yeah, and the way we do it is very easy, kind of simple. What you first do is you notice that if you restrict yourself to FLO unitaries that preserve some state, so here they preserve the all-zero state, then you can keep track of the phases of these guys very simply. If I had an FLO unitary where 0 was not an eigenstate, then actually K0 could end up being orthogonal to 0 here, and I would get 0, and I wouldn't know anything about the phase. But for guys where 0 is an eigenstate, I can keep track of the phase. And this has nice properties. The math ends up working out nicely. So okay, we first restrict our attention to FLO unitaries which preserve 0, that have 0 as an eigenvector. And these guys, we can keep track of the phase easily. We then have some stuff left over, which is this thing, it turns out, in the middle. And if you know a little math, this is called a Cartan decomposition of the group of FLO unitaries. It's very classical math from 100 years ago or so, I think, maybe more. Yeah, so I have a guy which preserves the phase here, I have a guy which preserves the phase here, and I have this bit in the middle in my Cartan decomposition. Yeah. Good. So essentially, yeah, I keep track of the phase of K1 and K2 easily, and I keep track of the phase of the thing in between in a slightly more complicated way. This gives us a nice way of representing arbitrary FLO states as just a passive guy. So this thing preserves 0, K preserves 0, and this A guy from before, all acting on a vacuum state. So this is like what you would actually store in memory in your computer if you're trying to do one of these simulations. And yeah, then we have algorithms that let you do all the things you want to do on this state if you want to. Fantastic. So this passive active form keeps track of the phases. You can do simulation of FLO things and add them up because you know the phases. Fantastic. This, by more or less known results, we had to do a little bit of work, but mostly by stuff that people had already worked out, gives you an algorithm for computing Born-Row probabilities of quantum circuits, which are FLO plus a bunch of non-FLO controlled phase gates. So this setup is universal, and it's classically simulable essentially if k is not very big. So the only super polynomial part of the runtime of this algorithm is this psi here, which is the product of all the extents that you get from these controlled phase gates. So this guy is going to be exponentially large in general as a function of k. Everything else here is polynomial. If you remember back many slides, and I'll be impressed if anyone does, I mentioned some trick about flipping gadgets around and how this is a small optimization. If you do this trick of flipping gadgets around, this cubic term here just becomes k cubed rather than k plus the number of qubits cubed. So you can remove n from this cubic if you want to by this flipping trick. Fine, so this is good. We have what we want. We can use FLO to simulate stuff which is nearby FLO. And the runtime, this is what I said already. You gadgetize all the non-FLO gates, you decompose the inputs to the gadget, and you do some sampling stuff. The runtime for a single non-FLO gate looks like this. So if I add a maximally non-FLO gate, which is actually a CZ, my runtime doubles. And if I add something in between, a controlled phase gate with a phase between 0 and pi, then the runtime cost goes up a bit. And then the runtime for the overall algorithm will be this multiplied together for each of the gates, the non-FLO gates. Cool. This is a quick comparison with the competition. So I told you a lot, way back at the start that you can do standard state vector simulation where you just store a list of 2 to the n complex numbers, essentially in runtime 2 to the n, and then you pay some cost for multiplying unitaries onto states, but it's okay. So in this algorithm that I worked out with Michał and Kamil, we have an algorithm that runs in 2 to the k, essentially, where k is the number of CZ gates. If your controlled phase gates are not CZ, but there's something else, then this will be a bit smaller, but okay, it's 2 to the something like k. So we have some advantage over standard simulation methods when k is less than n, which, okay, you can look for circuits that have this. There are some. I don't know if they're that interesting, but yeah. Yeah. So advantage over state vector simulation requires you to have essentially less controlled phase gates than you have qubits for us. Or if you do the same stuff for Clifford plus T, which is worked out over the last few years, then you need like 4 times k to be, k over 4 to be less than n. Fine. So I just have a couple of like open questions, things I want to think about in the future, and an Outlook slide left. So one of the things I want to think about is estimating things which are not Born-Row probabilities. So you could use these methods to estimate Born-Row probabilities. We pretty much know how to use these methods also to do sampling, like weak simulation or strong simulation. It's obviously interesting for physicists to estimate things which are not just Born-Row probabilities. So for example, we can estimate energies of Hamiltonians, for example, in some state. There are ways to do this. They're maybe not so smart. Maybe we can come up with smarter ways. This is one of the things I want to think about. I mean, what you do here is you just write your Hamiltonian out in terms of sums of, as a sum of Majorana-Fermi operators and do everything for each term in the sum. So it's not very smart and not very efficient, and there might be smarter, more efficient ways to compute energies or whatever. Another thing that I'm interested in is I showed you a few slides ago this fun fact that match gates or FLO is equivalent to log space bounded quantum computation. These two are computation equivalent. So this is a fun fact. But I've been investigating adding magic to FLO. This is what we've been doing, adding these non-FLO controlled phase gates. And I don't know if this is equivalent to something like log space bounded quantum computation anymore. So like, if there's no magic, this is true. If there is magic, suddenly, if there is non-FLO stuff in my circuit, but like a restricted amount of it or some amount of it that I can control, I don't know what is on the right-hand side of this equation anymore, and I would like to know. So yeah, here are some open questions, some future work, some vague ideas. I will say thank you for your time, and go back to this.
Thank you, Oliver, for a very nice talk. Yeah, we have time for questions or comments from the audience.
So this name, fermionic linear optics, where does it come from? And is it just linear optics with fermionic operators?
So it comes from this work by Terha and DiVincenzo. This is what they named it. It is something like the theory you would get if you had a bunch of non-interacting things which obeyed fermionic statistics, so they anti-commute, except they don't have any spin. So they're like spinless fermions, which is a little bit magic and a little bit spooky for physicists, but this is kind of what would be the case. Okay, so it's a little bit of a strange name, but they behave like spinless fermions, essentially. Yeah. I think Michał probably knows more about this than me. There are some like experimental setups that do vaguely resemble this, right? But they're a bit weird.
I think for fermions not so, I mean, people are trying maybe, but with passive transformations, then that would correspond to like standard linear optical transformations in photonics. So I maybe just comment that those are just analogs of just bosonic Gaussian transformations. Like when you have non-linearities. Yeah. Other questions?
So you said that this FLO without any magic is expensive when I have a lot of CZ gates.
So CZ gates are magic. So FLO is cheap, and then it gets expensive if you add magic. Yeah.
Okay, but this graph was there before when there are some gates that are close to FLO? Maybe a little
do you
bit
mean
cheaper.
this guy?
Yeah, yeah.
Yeah.
So how much can I do with those cheap gates? Yeah.
Okay, so you can do anything with those cheap gates, because if I have a controlled phase gate with a very small phase, I can just multiply all those together and get a controlled phase gate with a large phase, right? But then the problem is that the cost will multiply for each of the gates in your circuit, and this number will become large, right? So, I mean, you can do things with very small controlled phase gates, but you will probably need a lot of them, and then the cost will become large, I think. Yeah. That's okay. One of the things you can do with controlled phase gates with very small phases is coming up with estimation of stuff based on the Lee-Trotter product formula. So there's this formula that say if I want to exponentiate like h1 plus h2, I want the unit tree which is Hamiltonian 1 plus Hamiltonian 2. Then what I do is I do e to the h1 over n, e to the h2 over n, and multiply that together n times. I get a good approximation to e to the sum, right? So then what you get, because you divide each one by n, then you get a lot of very small controlled phase gates in your circuit. That is one thing that might be sensible to do. But yeah, I don't.
Okay. Other questions to Oliver? I maybe have one. So can you maybe comment on like the difference in the exponents between like cost in stabilizer formalism when you supplement it with magic states and FLO?
Oh, this side? Yes. So T-gates, if you're doing Clifford simulation, T-gates are cheaper essentially than doing controlled phase gates for FLO. I have mentioned this to a few people, and the best answer I think I got is that T-gates are not very powerful, essentially. So who did I speak to? I spoke to Hakop Pashayan, if you know him. Okay. Yeah, so he's kind of an expert also in Hakob. Yeah, he's an expert in this stuff, and his answer was essentially that T-gates are rubbish, and you need a lot of T-gates to do anything useful. So the fact that this is cheaper for T-gates doesn't really mean very much. You just need to shuffle loads of T-gates into your circuit to get anywhere. But I don't know if that's entirely true. It might be true, but this was his intuition. Yeah.
Okay, thanks.
So with this FLO, you have any restrictions on the number of qubits you simulate, or it's general? Because you mentioned that there are some special cases for 4 qubits that you have some nice theory or something, but does it matter at all here in this statement?
For our algorithms, no, it doesn't matter. For our algorithms, it's convenient if n is even. Okay, it doesn't have to be, but it's convenient if n is even. In general, to get like efficient classical simulation, you want your number of qubits to be, like in FLO, you want the number of qubits to be polynomial in like your difficulty parameter. So, you know, if my problem is, I don't know, route finding through some city or whatever, I want the number of qubits to be polynomial in the number of cities or whatever, you know. Yeah, I don't want, if I obviously have an exponential number of qubits, then I can't do things anymore. It has to be polynomial. But I can do whatever I like with FLO as long as the qubit number is polynomial. And yeah, so here for our algorithm scales in n. The only scaling is essentially n cubed, right? So we can do things as long as n cubed is small enough that we can get answers. Yes?
So you said previously that you can get rid of this k.
Yeah. No, you can get rid of actually the n in this one.
Right. Okay. So,
Sorry.
But still, you said that you can do it, and is it just gain, or is there some cost you pay in other places?
Oh yeah, so the point about this formula is that this number, this order of here, is multiplied by psi star, which is huge. So what will happen if you do this trick I mentioned earlier is you'll get a k here, and then you'll get, inside this order of, you'll get a plus something in n cubed, but the point, which will be some cost. But the point is that that thing in n cubed will not be multiplied by psi star anymore, which is huge. So I'll end up paying this cost like without it being multiplied by psi star. So it will be there, but it will be much less than this, because this algorithm is only relevant really when psi star is huge. Yeah.
Okay, if there are no more further questions, however, let's thank him again.
Thank you.